So let's look at an example of computing the matrix exponential. In order to solve a initial value problem. Okay, so let's say we have a matrix A, which is a Jordan block. So 3, 3, 3 along the diagonal, 1 along this sort of diagonal just above that. And then with initial data, x0 is, so actually let me just make this a 4 by 4 matrix. 3, 3, 3, 3, 1, 1, 1, 0, 0. Okay, so 7, 5, 3, and 9. Okay, so A can be written as 3 I4, which is this identity matrix of 4 by 4 identity matrix plus H4, and we know that H4 to the 4th power is 0. Okay, so so we know just from the general discussion we had, right, that the solution of this initial value problem is expressed in terms of the exponential of a times t. It's like multiplied into the initial solution, or the initial data, if you will. So x of t equals e to the at times this vector 7, 5, 3, 9, right, is the solution, well, is the solution. Of the IVP, initial value problem. Okay, so I have to compute e to the at. Okay, so e to the at is equal to e to the 3t identity plus t times h4. Okay, and because these two matrices commute with each other, I can write the exponential of the sum, right, as the product of the exponentials. Okay. Yes. So this is 3et, and then the identity part sort of just falls out. So this is 3 to the et times the identity, right? And then this is e to the t4. Okay. And I can actually drop the identity term, so it's e to the 3t, and then th4. We know that the 4th power, that vanishes. This is just the identity plus th4 plus t squared over 2 h4 squared plus t cubed over 6 h4 cubed. All right, and then I have to multiply it by, well, okay, right. Okay, yes. So, so h4, right. So let me just write this down. Okay. So this is going to be, so the solution x of t is going to be e to the 3t times the matrix, which is going to consist of the diagonal entries. All right, and then th4 is just this diagonal of t's, just up 1, right? Then you know that h4 squared, right, shifts up by 1 diagonal. So this is the t squared over 2 terms, t squared over 2. And then the last one, again, shifts up 1 more, which is the final one here. So this is t cubed over 6, and then the rest of them are 0. and then this is multiplied into the initial data, which is 7, 5, 3, and 9. Okay, so that's the solution. And you can write this down explicitly. All right, so this looks like 7 e to the 3t plus 5t e to the 3t plus 3 over 2 e to the 3t plus 3 over 2 t squared. Sorry, there's a t squared here, so this is a t cubed e to the 3t. And then this is a 5e to the 3t plus 3t e to the 3t plus 3 over 2 t squared e to the 3t. And then this is a 3 e to the 3t plus 9t e to the 3t. And then there's a 9e to the 3t here. All right, so that's what you get just by sort of multiplying these entries out. Okay, so that's sort of a relatively straightforward example. And then the point is that so this is just the case where A is a particular Jordan block, right? And then if you want to do this in full generality, then what you have to do is the following. So more generally, so in full generality, right, we have the Jordan canonical form. Okay, where so you can write A is equal to PC P inverse, where C is a block diagonal matrix consisting of Jordan blocks. Okay, and then you can check that if you have something like this, then e to the at is equal to p e to the ct p inverse, and if C is this kind of Jordan block like structure, okay, this block diagonal, let's call it J1, J2, all the way up to JK, right, then e to the at is going to look like p times e to the j1t, right, as a block, e to the j2t, and then the last block is e to the jkt. Okay, and then there's a p inverse here. All right, so the basic idea then is that you put together, it's like all the special cases which we talked about before, right? And you get something like this. All right, and so we've already seen the special case of how to compute the exponential of t times a Jordan block, right? So it's a question of putting everything together once you're given a Jordan canonical form representation of that matrix. Yeah, so that's basically what you need to do in order to compute the matrix exponential in service of trying to solve an initial value problem consisting of a system of linear differential equations. So let me just stop here.